Hello, hello, hello. Good evening, good morning. I don't know what time it is for you. But we're back doing another video, and we're working on chapter 10 still, group homomorphisms. There's a lot going on in this section, so make sure you read the textbook. And I'm going to give you the highlights here. Maybe not every detail to every proof, but really work on the homework early and often. So let's get started. All right, so we know what a group homomorphism is. It is just an operation preserving map between groups. And I gave you some examples last time, but here's some more that might be cool. So let's call this one D. It's going to go from something called R of X to R of X. Here, this is the polynomials of finite degree with variable x and real coefficients. So these are polynomials finite degree and coefficients in the real numbers, so real coefficients. And what am I going to do? I'm going to take a polynomial and I'm going to map it to its first derivative. Okay. Oh, the group operation here is addition, right? So we know that the derivative of f plus g is equal to the derivative of f plus the derivative of g. So we know this is a homomorphism, right? So here, d of f plus g is equal to f prime plus g prime, and that's equal to d of f plus d of g. So it's a homomorphism, right? It preserves the group operation. So the question is, what is the kernel of this map? Well, it's all the polynomials whose derivative is 0, right? What's the identity in this thing? It's additive identity. So these are all constant polynomials. Okay, so that's interesting. Later we're going to see that, and I've mentioned this before, but the kernel of a homomorphism is a normal subgroup. So if we mod out the real value or real coefficient polynomials by this kernel, what do we get? Basically, we get all polynomials that are the same up to addition by some constant. Okay, so keep that in mind because we're going to do another interesting example here. Let's call this I. Now we're going from the polynomials with real coefficients to the factor group that we get by dividing out by the kernel of the homomorphism above, right? So I'm going to take f, and I'm going to map it to the indefinite integral of f, okay? Remember, these are only well-defined up to in addition or by a constant, right? But if we mod out by all constant polynomials, right? That means that all things that are related by, all polynomials that are related by a addition by a constant will be the same in this factor group, and so that makes this well defined. Okay, and we know that the integral symbol works on when you add, right, functions. So here we know that integral of f plus g is equal to the integral of f plus the integral of g. Okay, so we know it's a homomorphism. And what is the kernel? Well, it's all polynomials whose integral is a constant. So it's just the zero function, right? So here the kernel is trivial. And that means that this is a one-to-one function, right? One-to-one homomorphism. Which seems a little strange, right? But maybe not, right? How many polynomials do you know that are the same, have the same, that aren't the same, that have the same integral? Well, it might up to addition by a constant, but we're modding out by that. So this factor group makes it one-to-one. All right, so there's a theorem in your textbook. This is theorem 10.1, or at least a mixture of theorem 10.1 and some other stuff. Just some properties of homomorphisms. Homomorphisms send the identity from the domain to the identity of the range. Okay, we already knew that from isomorphisms. There's no difference here. You know, because it's operation preserving, you have to preserve the order, right, of the identity. Well, anyway, okay. Here, right, this is telling us that two elements in G map to the same element in G bar if and only if they're in the same coset of the kernel. Okay, that's cool. And then, I've already said this before, it turns out that the kernel of a homomorphism is a normal subgroup. And it's if and only if, right? So if you want to find a normal subgroup, it's going to be not only is it well, it has to be the kernel of some homomorphism. Okay, so this is like an if and only if. So maybe I'm gonna give a little small shout out to the proof of some of these things, but the first one's obvious, okay, but I don't know. just do it again. So phi of the identity in G, well, the identity times the identity is the identity, and this means that this is why do we keep using lowercase g's? Okay, so we've shown that the image of the identity is itself squared. So I can use cancellation, right? Cancellation. Basically just multiply both sides on the right by the inverse of whatever that is. And what you get is the identity on one side is then what's left on there. So that worked out. Okay, about this next part. Well, let's go this way first, I guess. It's the easier way, maybe. So if A times the, or if the coset of A, sorry, the coset of the kernel with representative A is the same as the coset of the kernel with representative B, that's if and only if right, that's if and only if A inverse B is in the kernel. Okay, so that means that phi of A inverse B is the identity. Okay, but that's by property 1 if this is equal to the identity. And so that means that sorry, wait, that's not what I wanted to prove. That's oh yeah, sorry. This is I meant to say that this is not the identity. We don't know that's the identity. This is oh wait, yes, no, that is okay. It's in the kernel, so if I take yeah, that's the identity. But that means by the fact that it's operation preserving, right? I can distribute essentially this phi symbol, and so that means again that this is true. Okay, so that's one direction. This way, right? I can basically just go backwards, right? This implies that 5 A inverse B is equal to the identity, and that means that A inverse B is in the kernel, and that's what we needed to show, right? So all those previous steps were reversible. So that's supposed to be B. That's a check mark. Check. All right. And number 3, right? What about kernel of a homomorphism? Is it normal? well, this I think is proven as a separate theorem in your textbook, but you know, it's kind of quick. So let's think of this more of as a proposition. So let's say H, let's let H be normal in G, right? We want to show is H equal to a kernel of some homomorphism? Okay, question mark. Well, yes, it is. I mean, take phi to just be the canonical map, right, from G to the factor group, and H will be the kernel, right? So take G and send it to GH, right? And H equals the kernel of phi. Okay, so if you're normal, then you are the kernel of some homomorphism. Now, this is not what we stated. This is the converse, right? But let's just say we are a kernel of a homomorphism. Okay, is this normal in G? Is the question, and we need to show that A kernel phi A inverse is a subset of the kernel, right? That's how you show, one way to show something is normal, okay? So let's take anything of the form A K A inverse, where K is in the kernel. Let's take phi of that, right? So this is if, let's see what that is. Well, it's equal to 5A, 5K, phi of A inverse, which is the identity, right? Whenever A is in G and K is in the kernel, right? So therefore, A, K, A inverse is in the kernel, right? So that's what we need to show. Cool. All right, theorem 10.2 has a lot of stuff in it. Essentially what it says is that homomorphism preserve things that are, you know, groupy, okay? So if it's a structure that a group has, homomorphism preserve that bit, or most things, right? So if, for example, a group is abelian, right, and you take a homomorphism from that group into some other group, the image of the domain will be also abelian. The image of a cyclic group is cyclic, things like that, okay? I'm not going to prove all of these things. I think that sort of goes a little too far, but I will, you know, so let's just take for granted this one. Essentially, this all stems from the fact that, you know, homomorphism preserves the group operation, right? I mean, it's operation preserving. So group structures that have to do with group operations will be preserved. Okay, let's leave that. Now, this one here is kind of interesting. What this is saying is if the kernel is a finite number, then the mapping is n to 1, which means it takes n things and maps it to one single thing. Okay. A pullback is the inverse image of a normal subgroup. That's kind of a fun one. So let me just, I don't know, I think maybe I'll just state these things and say what they mean, and I'll leave the proofs for you to peruse. So so let me restate number 2, I think, in more detail. So number 2 here says if that if the kernel has order n, right, then phi from G to something else, okay, is an n to 1 mapping from G onto, see, I'm just going to go onto the actual image, all right? I don't really know, we don't know that this is onto from the outset, so what this is saying is that we know from the properties of cosets that all cosets have the same number of elements that are equal to the kernel. So this, this follows from the one of those, what was it? Number 2, did I say? This follows from number 2, okay, and the fact that every coset of the kernel has n elements, right? So the properties above, and that all cosets of kernel phi have n elements. Okay. All right. So what is a pullback? Right. What this is? Pullback, aka inverse image. This is just all. So if you want to do, say, the inverse image of a subset of the G bar. This is all elements in G that map to that. Okay, so what this is saying that if I take a normal subgroup, the pullback will also be normal. So if H is normal in G bar, then pullback of H will be normal in G. And, well, operation preserving is all we need. Okay, so I'm going to leave that one for that. Now, get to the cool thing that we want to use a lot. So we know that the kernel of a homomorphism is a normal subgroup, and so we can do the factor group. What is that factor group equal to? It's equal to the image, okay? And it's sort of the obvious isomorphism, right? What is the isomorphism? It's this. Okay, so here this says that what this is saying is if phi from G to G bar is a homomorphism, then the factor group G mod the kernel, right, is isomorphic to the image of G, right, in G bar. Okay. Okay, so we know what the mapping is, so let's show that it is first of all, we know this is a group because the kernel is normal, right? So this makes a group, factor group. Let's go ahead and define this. Of course, the image of the homomorphism is all, y values in the range, basically. Okay, so we take a factor group, or sorry, we take a coset of the kernel, map it to just the image, right? We need to show this is operation preserving, well defined, certainly, and operation preserving and one-to-one onto, right? So what do we want to show first? So let's do well defined first. So that means let's take G1 kernel of phi and G2 kernel of phi. Say those are the same coset. We want to show that those map to the same thing. Sorry, just in particular, we want to show that phi of G1 is equal to phi of G2, but this is exactly what we proved earlier, right? number 2 up here. So there's nothing to show. Right? We proved this already. Yay! So now let's try one-to-one, or operation preserving. Let's do that. Let's do the sort of technical ones first. Okay, is it operation preserving? Yes. Okay. So let's take that times that. Okay, where does it map to? Well, just by coset multiplication, that is the definition of coset multiplication, right? And that will map to, 5G1, G2, but 5G1, G2 is operation preserving, right? Because it's a homomorphism, so we get what we needed to show. This and this go to that times that. Yep. Okay. Now, one-to-one and onto. Well, let's show that the kernel is trivial. Okay, what's the trivial kernel? In this case, it would be whatever's in the kernel of psi. It needs to be the coset kernel of phi, right? That's the identity in this factor group. Okay, so let's take let k be in the kernel, then psi of k kernel phi is equal to e kernel phi, which equals phi of e, which is e. Okay, so that means that k is in that means if k is in the kernel of phi, it is in the kernel, then the factor group here is in the kernel of psi. So this is saying that kernel phi is a subset of the kernel of psi. Okay, I needed to show the other way. What if psi of a kernel psi equals the identity, right? In the image of phi, okay? Well, then that just means, right? It means that phi of A is the identity. We showed that that must mean that A is in the, well, that's exactly, it just means that A is in the kernel, right? And so that means a kernel of phi is equal to kernel of phi. Hence, kernel of psi is a subset of the kernel of phi. Right? So in other words, psi, this map here, let's call it psi, okay, takes a element in the factor group and maps it to an element in the image. But its kernel is trivial because the identity in the factor group is the identity coset, or equal to the normal subgroup there, kernel phi. All right, is this thing onto? Oh, of course it is. Onto? Yeah. Let G be in, or yeah, G. Sorry, let's say it this way. Let phi of G be in the image space. Okay. Then G kernel of phi, take psi of that, it maps to that, right? Since little g's for any G in big G. So that's a arbitrary element in the image space. Okay, so that's the first isomorphism theorem. There are two other ones, second and third isomorphism theorems that I'm going to prove for you in not another video, but maybe I'll just type it up and let you look at it that way. They're exercises out of the textbook exercise set, and I just want to show you them as examples, but I'm not going to assign those. Okay, so have a good one.